in case you missed the announcements, the we had a merger recently between the lecture series that's been running for abstract algebra over here and a reading group for Michael Artin's algebra textbook algebra that we have been reading over in a server called Simple Group. I will link some details later in the event chat. There's we've got a thread that tells you a lot. If you're interested in hearing more, down in the groups, rings, and fields channel over here. But in any case, what this means in practice is that we're gonna get started again. This we expect to be running this pretty regularly, weekly at about this time. Uh, the From what I understand, what the former organizers told us over at Simple Group, you had just finished up by talking about maybe permutation groups, and we're about to begin thinking about group actions. And one of the reasons why we agreed to this merger is because that's exactly where we were at in our group as well. Now, Artin does things a little bit differently than it seems like you did, so there might be some linear algebra stuff that is unfamiliar. If that's the case, or if you find anything unfamiliar, feel free to let us know. Um, you should be able to raise your hand for to request to speak if that's the way that you'd like to do it. I will also be monitoring the chat for questions that you would like to type in. If there are any administrative questions, I think I sort of hit everything that I needed to say, although it was a little bit chaotic. So no shame in asking for clarification. Um, but yes, we're gonna continue with this series today. Lonely Minecrafter is going to be talking to us about group actions, broadly speaking, and I'm sure we'll get a little bit more specific as we go in. But at this point, Minecrafter, the stage is yours.
Thank you. Uh, so Merry Christmas and Happy New Year to everyone. We are going to start today, broadly speaking, group actions. So, with group actions, we are going to uh, look into first in Artins up to chapter 5, from 5.1 to 5.4. We uh, broadly did uh, symmetry on like in a plane, triangles in a plane, points in a plane, etc. So in this, we are going to see abstract symmetry. So that's basically the motivation for going forward with this content. So we will start with that notion. So there is an example for that, and then we will go into group actions itself, which is all called as group operation in Artin. So I will be using group action. And is it loud enough now? Okay, so what I was saying is that I will start this lecture by going about thinking how to go from geometric symmetry to an abstract notion of symmetry. So we got a couple examples for that, and then we'll go over the definition of group action. So Artin actually calls it group operation. So I will be using both group operation and group action interchangeably. So keep that in mind, and then we will go over orbits, stabilizers, few theorems related to that, important ones, and then we finally have one correspondence theorem, so we will end with that. So that's the overview of today's lecture. So can't see this. Yeah, so the references for today's lecture are a book. uh, Basically we are following Artin's algebra. So, and then another reference that I have used is Introduction to Abstract Group Theory. It's a lecture series by Krishna Hanumantu from Chennai Mathematical Institute. He also has videos on ring theory, field theory, and Galois theory. So, if you are interested, you may look at that. So, yeah, we can get started with the first topic, group operations. Yes, so uh, so far we have looked at symmetry applied to geometric objects geometric objects. Like if we take a plane surface, we have seen symmetry operations on triangles, on points, etc. So now we are going for symmetry, that is more abstract notion of symmetry. So one easy example which allows us to visualize as well as relate is if we take the complex plane, so we have a natural symmetry along the real axis. This is basically what we call as conjugation. So if we take conjugation, we either go from a plus pi to a minus pi or the other way. So which also satisfies two conditions I have written here. So conjugation is basically an automorphism of the field C. That is uh, automorphism, to recall, is an isomorphism from one object to itself. So in this way, what we are going to do is when we were talking about symmetry, we were talking about geometric structures. So when we talk about automorphisms, we will talk about algebraic structures. So one good way to motivate is given in the next slide. Yes, so we will take the group of order 3. So order 3 is a cyclic group, so it has the identity E and then the generator G. So we have three endomorphisms here. So one is the identity map, which maps each element to itself, and then we have the map phi, which maps identity to identity, G to G square, and G square to G. The other map is not a homomorphism. It is an uh, endomorphism which maps all the elements to the identity. So the other two maps, the identity map and the phi, here form an automorphism group of order 2. So when we talk about automorphism here, we are basically talking about permuting elements of H such that they are compatible with its structure. So that is what I was talking about, how automorphisms are related to algebraic structure, like symmetry is related to geometric structure. So this leads us to an operation which we call as group action or group operation. Next slide, please. Yes. Uh, so if we take any group G and a set S, we will define an operation on the set G cross S, where we take an element from G, an element from S. We will perform an operation on this. Basically, we will denote it as a product unless otherwise specified. So it will be a product. So G product S to GS. So the G belongs to the group G. The small s belongs to the set S. The set S is not a group. So, and then the GS, the product also belongs to the set S. So when we perform such an operation, we call it as a group operation or group action. So base for this group action, we must have it follow two rules. So it's one is that identity times any set element. So from this, identity comes from the group. Any set element S comes from the set. So E times S will must give us back the identity. Sorry, the set element S. So the second rule is that if we take two, second rule is basically like associativity. If we take two group elements G and G dash, uh, the order with which we perform the group action must not matter. So we can perform the operation first on G and G dash, or first we take G dash and S. So the order does not matter here. Uh, the direction of operation does matter, because what we have defined here is uh, left operation, but the order itself does not matter. So if we have such an operation defined where a group G is acting on a set S, then that we call that as the group operation. So the group operation product will also be in the set S and not in the group G. So the group operation actually has uh, many applications which we will see next. Next slide, please. So the actual plan for today's lecture was that I will be working through the examples live, but due to some issues, I was not able to share my screen. So I'll be going forward. I have actually typed the examples back into the original PDF. So first, we will be taking one simple example. We will take a group with two elements, E and G. So, and then we are taking the set of complex numbers. The complex numbers do form a group, but we are not considering it to be a group for this example. So, if we take the group action G cross S, yes, here we consider that operation here to be the conjugation. So, how we define it as E times alpha. The rules are satisfied because E times alpha will give us alpha, and uh, since there are only two elements inside the group itself, the associativity is also satisfied. So the next example that we are looking at is we are taking an equilateral triangle with three vertices A, B, C, and then we are taking a group of rotations. So we have three elements in this group. One is the identity, that is the triangle is not rotated, it is in its original position. R1 is a 120-degree rotation and R2 is 240-degree rotation. So when we talk about action on S, so G product S here will be applying rotations. So for each, now have listed out all the possible combinations. So E times A is identity times any vertex will not move the triangle. So E times A is A, E times B is B, E times C is C. Whereas if we take 120-degree rotations, that is R1. So R1 times A, that will rotate the triangle. I'm assuming clockwise rotations now. So R1 times A, that will give a 120 rotation. So the vertex A will move to B, B will move to C, C will move to A. So in that way, the R1 rotations occur. So R1B goes to C, R1C goes to A. So again, if I take R2 operation, that's a 240-degree rotation. So if I do R2 times A, in the 120 A will go to B, and then in the next 120 it will go to C. So A will go to C, the 240-degree rotation, or else you can also take it as minus 120 rotation. So in that way, R2B goes to A, R2C goes to B. But again, once here, the two rules that I have specified for group action are satisfied because identity times any set member goes to A, and then identity times any set member, that is E times A goes to A, E times B goes to B, and E times C goes to C. And then if we take two products, R1 times R2, it is 120 times 240, which gives us identity. So it gives us the original set member. If we take the other way, that is we take R1 times R2 product A. So R2 product A is C. R1 times C is A. So again, this condition is satisfied. So these are the two simple examples I have taken to show the action of group operations. So I have taken a triangle here and applied the group and shown it here. So next slide, please. So permutation. So in the very first slide, introduction slide, I have mentioned how uh, by taking automorphisms, we are basically permuting through the objects. So in that way, if you have carefully noticed in the previous example, we have basically permuted to the vertices of triangles. So in that, that is the main function of group action, say. So if we take group G and S be a G set, so this is one form of notation. G set means the set S has the G action. Then, so if we want to think about permutation, what we take an element G, so and then vary all the S, and then when we vary all the S, we get one map. So that map we call it as MG. So MG goes from the set S to S. It goes through all the members of the set S. So that is why we call it as a permutation. So mg of s is equal to g of s is the notation we will commonly use, and this map is a permutation. We go through all the members, and it is also a bijective function, so it will go through all the function. If you go look at the previous example of the triangle, you can see that in all the three for all the three group members, uh, E, R1, and R2, we have gone through uh, all the set members A, B, and C, all the triangle vertices. So that is why when we take about group actions, we are basically talking about permutations. So next we will have to look at orbits. Yes. If you have any questions so far, you may please type it in the chat. I'm looking at it. Not quite see why in general case it goes through all. Yes, why is it a permutation? Yes, if when we are talking about the group, we have both G as well as the G inverse. So if you why it is a bijection, basically because it goes. We can also have Mg and Mg inverse. So in that way, it is a permutation. So when we are talking about here we are talking about the map, we both have both the Mg as well as Mg inverse. So in that way, it is a permutation. I hope that was clear. So next we can go to orbits. Slide please. Yes, the E here is identity. So if we have a group G which acts on a set S, and which is a G set, then what happens is that when G operates on S or G acts on S, then it decomposes S into sets, or a set or sets, which we call as orbits. So the orbits are defined based on each set element. So if we take a set element S, and then so for the permutation map, what we took, we fixed the G from the group and varied all the set elements. But how we find orbits is that we fix a set element S and then we vary all the G, and then whichever G product S are in the group, uh, we we will take that as a single orbit. So there may be cases where we will have only one orbit, or we may also have multiple orbits. So a simple way to understand orbits is that when we fix an element S and then vary G, that is the group elements, it is where the i- orbit orbit of S is the set where the S travels under the action of G or operation of G. So we have some operation, we fix an element S and then we vary the group members. So that is where the uh, element S travels. So in that way, you can uh, probably understand orbit. Orbit of S, or another way to define it as the image of under all permutations Mg. So the permutations I defined in the previous slide. So that is another way of defining the orbit. Yeah, we can go ahead with the question. Yeah, sure. So basically, so far we have defined group action, the permutation, as well as orbit. So orbit, we can understand it as the set under which the set uh, orbit is the set where S travels. So if you fix an element S and then vary all the G, you take G product S for different elements G, then all the G product S at the as the operation result will be the orbit of S. So it is the way to understand an orbit. So to compute few orbits, I have uh, given few examples in the next slide. Uh, so yeah, if you take the equilateral triangle example, so here the orbit of A is E product A, that is the identity product A, R1A, R1A goes to B, R2A goes to C. So ABC is the whole set actually, which is also the same for orbits of B and orbits of C. So there is only one orbit in the from the previous example. So if you take another example, GLN of R, I think that is uh, yes, yes. That is in the next slide. I will come to that. Yeah, yeah. Orbits and equivalence classes. Uh, there is a theorem for that which I have discussed in the next slide. So uh, G equal to GLN of R. That is the general linear group, and then if you take the set of r cross r to n times. Then if you take the orbit of the zero vector, so GLN of R is n cross n matrices. So any metric we multiply with the zero vector, we will get the zero. So orbit of zero vector is just the zero vector itself. In orbits, we consider the set members. Yeah, set members. And next, if V is a non-zero vector, then the orbit is all uh, the whole r power n minus the zero vector itself for any other vector non-zero vector v, because when we are talking about the general linear group, if we take any matrix A, uh, sorry, if we take any non-zero vector that is not v, we'll be able to find a matrix A such that A times v will be some other result. That is the needed vector. So yeah, so that is the orbit of OV. And next next slide, please. Yes, equivalence class you were asking about. Uh, so we are now defining a relation. So if we take an orbit, it will have some set elements S, uh, and let us say S dash and some other elements. So uh, we say that two elements are equivalent if they satisfy the relation G times S equal to S prime. So Why this equivalence class is important, I have discussed in the next slide, but here I have given a simple proof of equivalence relation. So if we are talking about uh, the reflexive, it is true because E times S gives us S. So reflexivity holds. If we talk about symmetry, then G times S1 is equal to S2. So if we take the inverse, then G inverse G S1 is equal to G inverse S2. So G inverse G is identity. So identity times S1 is S1. So finally we get S1 is equal to uh, G inverse S2. So again, symmetry holds. In the similar way, transitivity also holds. So if S1 is, yeah, I'm not going to read through that, but it is an equivalent relation. So why this equivalence class is important is given in the next slide. So next slide, please. So previously somebody else must have covered that an equivalence relation will have partitioned an entire set into disjoint equivalence classes. Uh, so basically, if we have uh, uh, some set, it will be disjoint equivalent classes. So and it can also be seen that this equivalence class and orbit actually denote the same. So this is because if we take some set element S and we see the equivalence class of this set element, so it is all the other elements in the set such that S is equivalent to T. So if we see that, then that must be of form T is equal to some group G times S. So T is equal to GS. But this GS will be in the orbit. So I have started from an equivalence class S, equivalence class of S, have taken the similar elements, that is S equivalent to T. So I have taken those elements. By my definition, those elements must be of the form T is equal to GS. But these GS belongs to the orbit of S. So when they belong to orbit of S, we can see that the equivalence class as well as orbit both denote the same. So that is why I wanted to cover. Artin actually skips through a lot of these steps. I don't know why, but I wanted to cover this here. Uh, so when we talk about any group action, the group action works on the individual orbit. That is, if we take a group action on some orbit OA, it will not send the orbit element from OA to some other orbit OB. So in that way, that is why we call it as disjoint. So it is also possible that we will only have one orbit. Uh, so when we have say only one orbit, in that way we say that G will operate transitively. So when we have only one orbit, then we are operating upon the entire set S itself. So, as I pointed previously about how equivalence classes partitions uh, the entire set into disjoint equivalence classes, same way orbits also partition the whole set into disjoint orbits under the group action or the group operation. Um, Orbits a generalization of cosets. When we are talking about, I'm answering the question that's in the chat. Uh, when we are talking about orbits, then you, the orbits are actually Cosets are disjoint group members. So cosets are basically you take a group, you take a subgroup of the group, and then you partition that group. Uh, that is how we form. Uh, uh, we take the partition and then we get a coset space, and then if that uh, if that subgroup is normal, then we say the whole coset space can also be a group, but uh, otherwise it's not a group. So orbit, on the other hand, we partition the set in which a group acts. So, uh, so I think we can actually like they are both very similar in their function. So I think it is okay to call them, but we will also have group actions on orbits. So, but I think it's okay to call them. I don't want to give a very sure answer because I'm not too sure about. Next, next slide, please. We are talking about. Okay, so we have talked about orbits. Now, next, when we talk about group actions, we talk about permutations, then orbits, and then stabilizers. So the next object is stabilizers. So uh, when we talked about orbits, we fixed a set member, and then we varied the group, and then saw where the group uh, saw where the element traveled inside the set. So when we talk about stabilizer, we want to see when we take a set elements, which group members do not vary under the group action. So basically, it is so uh, the uh, stabilizer is a set in which contains the set elements that do not vary under the group action. So if we take G product S, then it will always give us S. So one such stabilizer is easily the identity, but there may be other group members such that this relation holds always. So uh, orbits do not form a group but stabilizers actually do form a group. So it is very easy to see that. So we have the closure, which comes by the definition itself because E times S belongs to S. So S will be in the stabilizer group. So when we multiply, we always end up in that with that value. So identity holds, and then associativity inverse also holds. So they do form a group. I don't want to read the long equations and spend too much time on that because do I have 1 hour or 2 hours? Not sure how much time I have. Okay, okay, yeah, it's fine. I think, yeah. So next slide, please. Yeah. So as I said, for any group we take, the stabilizer of 0 will be the entire group. And then if we take a cyclic group of order 7, then if we take the stabilizer of 3, then uh, uh, only 1 will be in the stabilizer because 0 times 3 does not give 3. 1 times 3 gives 3. 2 times 3 gives 6. And then 3 times 3 gives 2. So on. Only 1 will be in the stabilizer. And then the third example I want to talk about is a group of rotations acting on dodecahedron. So this example I will talk here and one other place. So dodecahedron is a object with 12 faces. It has 12 faces, 20 vertices, and 30 edges. So if we take any one face, if we take any one face of a dodecahedron, and then for that face, if we want to find the stabilizer group, uh, then it is the 72 degree, that is 2 pi by 5 rotations. So when we are talking about rotations of a dodecahedron, we take it perpendicular to the face. So that is the axis that is going through the face. So it is the 72-degree rotations. Why 72? Because the face of a traditional dodecahedron will have uh, each face will have 5 sides because it is a pentagon. So every time you do a 72-degree rotation along the axis that is perpendicular to the face, we will get the same object. So that is another example of a stabilizer. And then the order of stabilizer for each face, that is you have 12 sides. So order of phase 1, order of phase 2, each face will be 5, and there are 12 phases. So next slide, please. So we have so far seen operating on a set. Next, we are going to use cosets. Yeah, next slide, please. So cosets must have been introduced in previous lectures, and so let H be some subgroup of G. Then the left cosets A times the subgroup H will partition the G. So that is what I was talking about. So when we are talking about partition, I think it is analogous to the how we partition the orbits, but I don't want to say the exact because I don't know. So I don't want to say like this is the precise way they are related. I don't want to claim that. Um, so we will call this all the A by H as a coset space G by H. Uh, so G by H is not a subgroup unless it is normal. But one interesting thing to see is that the group G acts on H, G by H, like it acts on any set member. So G by H is a set of cosets, but and G acts on G by H like it will act on any other sets. It can be easily seen that it also satisfies two rules. So if we take any element small g in the capital G that is from the group, then any coset capital C, then uh, the G times C, that is the group action G, G product C is basically all the G times the coset members, and that is G times small c. That is what contained in the uh, group operation. And if coset is some A times H, then G product C is G product A product H, the coset H. So in that way, it will satisfy both the group operation. G product C, sorry, it will satisfy both the identity. So E product AH is A times H, because when we say take E product A product H, then E product A will be A, so A product H. So identity is satisfied. The next one G1 G2 AH. So in both the ways it is again satisfied. So uh, it it is a valid group actions to talk about a group acting on a set of cosets. That is the coset space itself. So uh, in any coset space we take, G operates transitively. That is, the entire coset space will only have one orbit, uh, which is the orbit of the identity coset. That is identity times H. That is the subgroup itself. Uh, if we have the subgroup generate an orbit, if we have the subgroup generate an orbit, then the orbit will be the entire coset space. So the stabilizer of this coset space is also H. So when we talk about group operation here, if we take g times a times the coset h, then uh, we are not saying that there is no change in the product or the output. But what happens is that g times a times h will go to the same. Uh, sorry, I should be talking about the subgroup here. So H, the identity coset. So when we are talking about identity coset H, then there will be a change in the value, but it will go inside the subgroup. That is the what operation we do. The operation acts inside the subgroup. So maybe the subgroup has some five numbers, and then it will go from number one to number three in that way. So in that way, the operation occurs. So the coset remains the same, but the value of the operation actually does change. Uh, Next slide, please. So the plan for this section was to actually work out with the work out on slide, but since I'm not able to present uh, at the last moment, I had to upload my handwritten slides. So one I want to talk about one important example here. Are the letters too small? I'm not really sure. I can read them, but how about others? I think that's a bit better. Yeah. So we are taking the dihedral group D3. So D3 as an order 6. So uh, if we take the D3, if we recall the operation, it has the identity operation, and it has two rotations. That is rotation to 120 degree or rotation to 240 degree r square. In my previous slide, I have given it as r1 and r2, so I'm not using the same rotations everywhere. And then it has translation, that is which I've given as yes. So if when we take a s, we can actually translate to in three axes, but if we combine the translations with the rotations, we can remove the unnecessary variable. So instead of having like three different transitions, we can have s r times s, and then r square s for the different translations. So we will take a subgroup of this D3, which will be E and Y. Y is the translation, so I'm commonly denoting here. So E times Y. So if you take the order of H is 2, so now the order of D3 is 6. So if you take the cosets of uh, G by H, we will get three cosets. One is the identity coset, that is the H itself, which is E times Y. Next, which I have denoted as C1. The next coset is C2, which is R times H. So R times H gives us E times R, which is R itself. That is 120 degree rotations, and then uh, R times Y. That is the left operation. That is uh, we do a translation and then a 120 degree rotation. And then if we take C3, that is R square H. So basically 240-degree rotation and the translation. So in that way we have three cosets, and as you can see all the three cosets are disjoint. Disjoint and if we take a group operation G operating on G bar H, it is in the next slide. Yes, G operating on G bar H, then every element of G will determine a permutation Mg. So if we take the identity operation, so G has six elements. So I have shown here only four permutations. So identity permutation, one goes to one. Actually, I have taken each of these coset C1 as one, C2 as two, C3 as three. So C1 as one, C2 as two, C3 as three. So if you take C1, so identity. If you take identity E, so E times E is E, E times Y is Y. So that is no change. So no change across all the three cosets. So one goes to one, two goes to two, three goes to three. So next, if I do a rotation, that is MR, M subscript R. So if I do a rotation, then the operation will be MR is equal to R times the coset. So R times E is R, and R times Y RY. So coset 1 will go to coset 2. Here I'm talking about cosets. So the coset C1 will go to C2, and again if you take C2, C2 will go to C3, because in C2 we have C2 is the coset R times H. So C2 has members R and RY. So if you multiply C2 by R, we get R square and R square Y, which is basically the coset C3. So and C3 comes to C1, because if we take multiplication R times C3, we get uh, r r cube is a 360-degree rotation, which is the identity, and then r cube y. So r cube y is ey, which is y. So we get the identity coset. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. And then next, if we take mr square, 1 goes to 3. I think you see the pattern. 1 goes to 3, 3 goes to 1, and then goes to 2. So that is like two movements here. And then 2 goes to 3, 3 go, and then goes to 1. So that is like two movements here. And then if we take my, so y times e is y, and then y times y is y square. So identity goes to identity, 2 goes to 3, and 3 goes to 1. So in this way, I have not listed out other two, but other two will also yield unique permutations. All the four permutations listed here are unique, and each of the element will. So the group has six elements. We have six permutations. What we can see is that the symmetric group, if we denote these six permutations as P perm G bar H, all the six permutations, then we see that it is like equivalent to symmetric group S3. So what we conclude is that there is an isomorphic relation between each group member G to the permutation, that is S3. So that is an isomorphic relation between each of them. So we the D3 and S3 are isomorphic. So that is one nice examples to work out group operation on coset. So this isomorphic relation is actually important, and it will come back later in, in lecture. So after this we have theorem. Next slide, please. So there are two theorems. So this is proposition 1 and proposition 2. So we have a group acting on a set S. So we have some set element small s, and then we have gs be the stabilizer of s, and then os be the orbit of s. So we claim that is a bijective map between uh, uh, G over Gs to the orbit of S. So we claim that there is a bijective map which is defined by phi uh, A GS is equal to AS. Uh, so the proof, we basically check three things. First, we check that the map we are defining, that is 5 AGS is equal to AS, is well defined. So mm, to check it is well defined, we need to basically take two orbits. If we take two orbits here, that is G product GS and H product GS, we need to check that uh, when we take the map, we get G times smallest and H times smallest. So when if these two products are equal, then we can conclude that both the cosets we have taken are also equal. So here is where we will be using the definition from our equivalence class. So uh, the two cosets can be assumed as equivalence classes. So these equivalence classes, G product GS and H product GS, are equal if and only if uh, G is equal to H times G prime. G prime is some member in the stabilizer. So if G is equal to H times G prime. So this is the relation that we defined in the equivalence class and showed how equivalence class and orbits define the same. So now if we take the mapping from G product GS and H product GS, we'll see that GS equal to H G prime S. But here the G prime stabilizes S. So we basically get G times S equal to H times S. So our map is well defined. So to check this is a bijective map, we need to show that one to one and one to, that is injectivity and subjectivity holds. So that is given in the next slide. Yes, to check injectivity, I think yes. So we take the again the two cosets uh, G product GS and H product GS. So we take the map that we have defined. So we get G times H and H times H. Yes. So if we take the G inverse, so G inverse H S, G S is equal to G inverse H S. Then that product G inverse H must belong to the stabilizer, because the product of G inverse H times S is equal to S. Uh, so if we take H is equal to G times S, then that will the H must belong to the stabilizer, uh, to the coset G into GS. So since H is in the uh, G times GS, both the cosets we have taken must be equal. So this shows that the map we have taken is indeed injective, and surjectivity is basically given because whatever coset we take, there will be a product. So G times H will give us a map from G times H will give us GS. So surjectivity is basically given for our proof. So when these two injectivity and surjectivity is given, we can conclude that the map we have taken is a bijective map. So this theorem says that there is a bijective map between the coset space G product GS and the orbit OS. So this is a very important, because from based on this we will define our uh, next theorem. So Uh, the next theorem we will be talking about is the orbit stabilizer theorem. So for using the orbit stabilizer theorem, we will be using this proposition. So Before that, we have one more proposition. So proposition two, I will. The proposition two is very simple. Uh, so if we take a group G and a set S, and if we take two elements, so we take a set element S, and then we take the orbit of S, and then we take another element from the orbit. Then from the equivalence class relation, we can say that S dash equal to S for some group member A. So that we established that in the equivalence class proof. So what we want to say here is all the elements G in the group are of the form A times GS. GS is the stabilizer here. So A times the stabilizer. So it the coset A times GS uh, the will be of that form. And then the second part of this proof is that stabilizer of S prime is the conjugate group of the stabilizer of S. So the first proof is actually very easy. So uh, S prime is equal to G times S. So G we define as A times H. So in that way we H is the stabilizer. So we get uh, the result that is needed. A times H, A times small s. The small s will be in the stabilizer of S. So we get A times GS. So in that way, the first proof goes, and then if you take the second proof, S equal to GS prime is the condition that we have take from the equivalence class relation. So if we take the inverse, G inverse, then H is in the stabilizer. So if we take the H out, here we are taking H at the front because when we are talking about cosets, then G inverse S will be inside a coset. So H we are taking to the front, and then we multiply the whole thing by G. So GH G inverse is equal to GS prime. So GS prime is the our original S value. So GH G inverse is of the form of the conjugate, so that is G, uh, GS, and sorry, not prime, G inverse. So G, GS, and G inverse. So it is of that form when we are talking about the person. So in that way, the statement two is also proved that the stabilizer of S prime is the conjugate subgroup. So uh, for conjugate subgroup, it is the needed condition. So we have basically covered the group operating on cosets. So we have defined how some group will operate on a coset, and then we have taken how when the group operates on the coset, uh, how the conditions are still satisfied over the coset space, and then we have taken a simple problem on, and then we have covered two important propositions. So based on these two propositions, we will cover the orbit stabilizer theorem. So yes, I think we can go ahead now. Uh, Next, we have counting formula section, that is basically with the orbit stabilizer theorem. Next slide, please. So if we uh, take a group G, and then if we take a subgroup H, we know that the subgroup H and all the cosets of cosets we generate using H will have the same order or the same number of elements in them. If we are talking about the finite groups, so we are talking about finite groups when we are talking about uh, orbit stabilizer theorem mostly. So then we have a formula. We call it as Lagrange theorem. So where the order of the group G is equal to order of H, that is the subgroup which we form the cosets. So order of group G is equal to order of the group H times the order of the Poset space. So it is a very nice theorem which we use to compute the size of groups or size of Poset space. So if we have any two values, we can compute the third one. So for computational purposes, we use this relation, and then uh, from the proposition one of the previous slide, we established that there is an isomorphism. There is a bijective map between G product H. So H, uh, G product H and the orbit of S. So H, uh, when we are talking about H, that is the group with which subgroup with which we generate the posets. That will be isomorphic to the stabilizer, which we established in an older slide. I'm not sure where I did that, but I did that. So if we talk about that, so G product GS is a bijective to orbit of S. So sorry, G over GS to the orbit of S. If we take their orders, then they must be same because that is a bijective map. So if we take a bijective map, then there must be same number of elements in both of them. And then again, if we come to H and the stabilizer, again we must have same number of elements in both of them. So we can what we can do is that we can actually replace the two values. It is in the theorem, and we get a new theorem which we call it as the orbit stabilizer theorem. So order of G is equal to order of the orbit of S times the order of orbit of G of S. So this relation we call it as the orbit stabilizer theorem, and for each set element S, we will have a unique relation. It may be unique or it may not be unique, but we will have uh, a relation for each orbit. So if we have like 10 orbits, then we will have 10 stabilizers. So then we will have 10 equations. So when we are so this relation is basically the orbit stabilizer theorem. And when we are talking about finite groups, we also have a term called as index. So index we define it as in the square bracket G colon H. H is basically the subgroup which we use here. We have used as GS. So G colon GS basically gives us like the size of the subgroup or size of the coset we have taken. So uh, basically when we are talking about finite groups, so then the index G colon GS is also same as the orbit value. So we can replace that, and we basically get two relations when we talk about orbit stabilizer theorem. So first relation is that G colon GS is equal to the order of G colon GS, that is the index of G colon GS is equal to order of orbit of S, and then the second equation is order of the group G is equal to order of the orbit of S times the order of stabilizer of S. So this relation we call it as the orbit stabilizer theorem, and then if we know the orbit orders, then we can also compute the actual set. So if, when we talk about orbits, we know that orbits partition the entire set into disjoint orbits. So when we take the complete sum over all the order of the orbits, then we get the order of the entire set itself. So I think there are three relations here which must be known. So the proof of this theorem actually lies in the proposition one, which was covered in the previous slide. So next slide, please. So next we will. I wanted to work through this problem actually, but yeah, we'll go forward with this. So again, we're taking a dodecahedron. So dodecahedron is a 12-sided object. Uh, Last time we did not compute the order of all the rotations. So what I wanted to uh, the group we are taking is orientation preserving symmetries, which are basically rotations of the dodecahedron. So when we are talking about all the rotations of dodecahedron, it has too many faces, too many vertices. So if when we talked about the triangle, we manually computed all the rotations and translations, but for a dodecahedron, it is not possible. So here we will use orbit stabilizer theorem to our advantage and compute it. So like the previous example, if you take the stabilizer, when we take the stabilizer of any face, so let us take the top face here. So if we take the top face here and we stabilize, so when we are talking about stabilizing the top face perpendicular to the top space, so we take the axis that goes perpendicular to the top space, so to the top and the bottom. So if we now when we are talking about stabilizing, the object shape must be preserved. So when we rotate the object, so let us assume counterclockwise rotations. So when we rotate the dodecahedron axis, we have assumed that is the axis to the uh, top of the dodecahedron. So we the top face. Assume that there is an imaginary axis going through the top face. So we rotate the dodecahedron through this axis in a counterclockwise direction. So we cannot rotate it in any degrees we want. If we want to preserve the symmetry of the dodecahedron, so if you want to preserve the symmetry, then we can only have five rotations. That is the five sides of the pentagon. So uh, when we rotate through the each to preserve that symmetry. So when we rotate through each, we get 2 pi by 5, that is 72-degree rotation for each 5 phase. So for that particular phase that we have taken at the top, we have the stabilizer order to be 5. So the order of G of S for the top phase is 5. So uh, now we see that for a coset space, we concluded that G acts transitively. So uh, the order of the orbit is 12 because there are 12 phases. So uh, there are 12 phases and they attach transitively. So uh, we can compute actually the order of the group itself, the number of total rotations. So uh, for the there are 12 phases, that is 12, and which is the order of the orbit, and there are five rotations. So 5 times 12 is 60. So the order of uh, the group being the rotations of dodecahedron is 60. So that is one computation. So this is not the only computation actually. So if we take the vertices, so if we take each vertices, uh, the vertices are stabilized if we take any one vertex, uh, the order of the stabilizer is 3. So if we take if the cursor pointed, if we take that vertex, if we do one rotation, that is bring the next phase of next pentagon, then we will get one. So we have one identity and then one, and then in that way uh, we have to skip one and go to the next one. So in that way we have uh, three. The stabilizer order is 3. So we have computed the group order is 60. So from that we can actually since the group acts transitively on the orbits coset space, what we can find is that the order of the orbit of vertices is 20. So because the group order is 60, the stabilizer order is 3. So 60 divided by 3, we get the order of the orbit space, that is the order of orbit of V, that is 20. So and then similarly for edges, if we take the for each edge, it is the stabilizer is 2 and the order of orbit is uh, 60 divided by 230. And then so we have taken here in this example till now we talked about the group itself acting on the set, that is the faces of dodecahedron, the vertices of dodecahedron and then the edges of dodecahedron. So next, if we uh, if we take a subgroup acting on the set, what will be the relation? So if we take H, let us assume H is the subgroup of the group G. So the group G has all the rotations of possible for this dodecahedron we have taken. So let us take H. Uh, Let us assume that H only consists of the rotations for the top dodecahedron. So we have, sorry, top face of the dodecahedron. So we have top face of the dodecahedron, and H consists of all the rotations. That is, we concluded previously that the order of this group will be five. So the H consists of five elements. Uh, so now we want to find so what happens when H acts on, that is H operates on all the 12 phases. So when we are talking about H operating on all the 12 phases, so what is the relation we have? Uh, the, uh, the first is uh, uh, in H we have 72-degree rotations. That is 2 pi by 5 rotations, five of them. So we have those rotations, and then when we take the Lagrange theorem, we see that uh, the order of the orbits that we take must either be 1 or 5. There are no intermediate option, because uh, uh, the total uh, order of the set is 12. The set has 12 faces. What we see is that uh, when H acts on S, the top face is fixed. Uh, the top the top face of the dodecahedron is fixed. The bottom face of the dodecahedron is also fixed, because we cannot trans when we rotate through the top axis, we cannot move the when we rotate through the top axis, we cannot move the top face to any other position. So the top face is fixed as well as the bottom face is fixed, because the bottom face also cannot move through to any other position when we do the 72-degree rotation. But there are 10 other faces around the dodecahedron. Uh, so five of them, that is the top five will move amongst them. That is the top five pentagons will move amongst uh, move through them, and then the bottom five will move through them. So we get uh, those are two separate orbits. So totally we have the orbits of order 1, that is the top phase orbit of order 1 of the bottom phase, and then the top 5 pentagons will form one orbit, as well as the bottom 5 pentagon will form one orbit. So we have four orbits, one orbit, two orbits are of order 1, and two orbits are of order 5. So if we take the sum of all the orbits, we get the orbit order as 12. That is, the 12 is also the order of the set. So if we take the orbit stabilizer theorem, the third relation which we saw holds. So this was when a subgroup acted on the set of faces of a dodecahedron. So in this way, we can also have like you can also see how some subgroup acts on the vertices or edges. I have not discussed that here. Uh, so next, to generalize this notion of uh, the order, there is one proposition given in the next slide. Next slide, please. So we have two subgroups of group G, H and K. So what we want to show is that all the three are finite. So we have index of H colon H intersection K, then it will be less than it will be almost equal. That is, it will be almost same, or it may be same to the index of G colon K. So it is a very simple proof. So I will quickly go through this. I think because we have one more section actually. Uh, so if we take the coset space G over K to be the capital S, and the group K to be small s, then by the previous proposition, index G colon K will have the same value as the order of the coset space S. So that is one relation we have taken. And next, what we do is restrict the action of G to H. So first we have the G action on the coset space. Now we have the H action. So if we take the stabilizer, the original stabilizer will have the original space, original S will have the stabilizer as K. Now we have the stabilizer as H intersection K, since we have restricted the mm, group action. So if we take any orbit in the new group, so orbit of H, so some any orbit, then this orbit must be a subset of S. So orbit will have some order. This order will be less than S. So if we can finally say that, uh, and this orbit will also have, from the previous proposition, same order as the orbit of the order of this orbit will be same as the index of H colon H intersection K, because that is the new coset space we are looking at. We have restricted to H over H intersection K. So that is the coset space we have taken. So this coset space will have the same value uh, as the orbit, and that will have the same index. So order of this orbit will be less than or equal to the subset. So if we are having uh, a transitive action, then this there will be an equality. Otherwise, it will be less than the set S, which has the value of index G colon T. So that is the simple relation here. And next, I will finally go through permutation representations. There is just one theorem in that section. Yeah. So so when we are talking about symmetric group, we generally define symmetric group as operation on the set S is of 1 to n numbers. So uh, there is also a permutation representation between any group G to Sn. So if we take in the previous example, not this one, the uh, dihedral group D3, we established that there is an isomorphism between D3 and S3, the symmetric group of a symmetric group S3. So there is an isomorphism between D3 and S3. So that was we can assume that to be somewhat of a motivation to why we want to study uh, homomorphisms from group to the symmetric group. So if we take any group action G acting on Sn, uh, then we take the map homomorphism mapping phi G to be the group action. So that is the function that we define, and what we claim here is that this function is there is a bijective correspondence between this function. So the function that is on one side we have the all the on one side we have the collection of all the operations, group operations of G on S, or the group actions G on S. On the other side we have all the homomorphisms from the group G to the permutations of the set S, that is the Sn, the group Sn. So we claim that there is a bijective correspondence between this relation, the group operation, as well as the homomorphisms from the group to the permutations, and we define it through uh, the homomorphism of G is equal to mg. If you remember the initial slide, we defined mg to be uh, uh, when we are operating, we take mg of s, where s is some set element. So if we recollect mg, we basically fix an mg, fix a g from the group, and then vary through all the set elements s. So mg is g times s. So in that way we define the mg, and then phi g is phi g of s. So we say that these two relations are equal, and there is a bijective correspondence between these two. So Artin actually does not go through the entire proof, but I have tried to write the entire proof. So, next slide, please. So first, to define these two first we need to verify that these two operations are indeed valid. So first, if you take mg, so mg is valid because mg is a group operation, because the identity holds e times s is s, as well as if we take mg g prime, so m subscript g g prime times s, that is uh, taking two elements at once. We can also take it as separate operations. So that is what it is. They are the two conditions that we need to see for the group action. So it is a valid group action, which we also established previously. And then next, we want to check for the homomorphism. When we check for the homomorphism, we need to verify the axiom that phi xy is equal to phi x times phi y. So how we verify it? We just check that the group action is indeed correct. So we use the group action here. So we take mxy is equal to my. So we need to prove this. We take the values. So mxy of s is xy times the set element s. And if we see the other side, we have mx times my of s. So that will be mx times y of s. So that will be x times ys. So on one side we have xy times s, and other side we have x times ys, which by associativity are equal. So the homomorphism we have is indeed a valid homomorphism, and it is the steps are pretty trivial. So next, to prove that we have a bijective correspondence, what we will do is we will take mapping from both sides, that is lambda and delta, which I had shown in the previous slide. Yeah. So one side, if we go, we will take lambda, other side delta. So when we see that the operations are actually pretty trivial. Uh, so when we start from one side, so if we start at the group operation, and then we have some value, we go to the homomorphism, and then come back to the group operation. We see that we end up with the same value, and that, if we do the other way also, we would end up with the same value. So when with this we can establish the bijective correspondence, which I have shown in the next slide. The next one, please. Yes. So if we go from the homomorphism to the group action, so that is the delta operation. So if we go from homomorphism to action, that is homomorphism is phi g of s. So group action is gs, is simply gs. Again, if we go from group action to some homomorphism, then it can be any homomorphism, psi g of s, or any homomorphism. But because of the way we define this problem, both the value of phi g of s as well as the psi g of s is the same. So we can conclude that a homomorphism maps we are taking while going the original homomorphism map, as well as the map when we go from the group action to homomorphism, is the same. And again, if we take the inverse, that is, we go from group action to homomorphism back to group action, again we get the same kind of result. So we have a group action, we go to homomorphism map psi, again to group action. We see that at the end, the product of both the actions are same. So we actually have a bijective map. So hence we have established the correspondence we have wanted. So this is the basically the correspondence between how correspondence between group actions by a group G on a set S, not a set, group action on a set S, and the homomorphisms, that is homomorphisms from the group G to all the permutations of S. So we see that there is a bijective correspondence.